So, hello everyone, it's me Saurabh Poril. So, I'll be hosting this event today. So, welcome to SEDS Talk Series of Nepal, Series 3. So, here we have today Justin Nguyen. So, he'll introduce himself about his program and what he's currently doing. So, I'll hand over this mic to Justin.
Hello, hi. So, my name is Nguyen. And presentation. So a little bit about me. I'm a fourth-year computer engineering undergraduate student at the California Polytechnic State University of San Luis Obispo. We call it CalPoly SLO, and I work at the CalPoly CubeSat Lab. I joined in November of 2016, and I'm currently the lab manager, and I do a lot of the electrical hardware design. These are some of my photos. So if you look at the left photo, that's me and my team after we finished one of our CubeSats, ISX. And the photo of the right is me with the former lab manager working on data. And a little bit more about me. So I interned at JPL in the summer of 2018. And I did a really big mission called Marco, which were the first CubeSats to fly into deep space. And they flew by Mars and assisted EDL with one of the landers by JPL called Insight. So I was the flight operations intern for Marco, and I was on console for the Insight EDL. EDL stands for Entry, Descent, and Landing. So the photo on the left is me inside of the space flight operations facility at JPL. It's really cool because it has a lot of those LED strips and dark lights. And the photo on the right is the Curiosity rover, which they have on display there. And then this past summer, I assisted the Liger Leadership Academy. It's this school in Phnom Penh in Cambodia, and they wanted to start a CubeSat program. So I flew over there with my professor, Dr. Four, and we assisted them with their ground station infrastructure and sort of plan their CubeSat development cycle so that they could maintain the program through the years and be successful launching the first CubeSats. Yeah, so that's the team on the left. And on the right, that's me when we had a couple days left and we went to Angkor Wat.
Cool.
Yeah. So I'll just talk a bit about what a CubeSat is, just in case people aren't familiar. So a CubeSat is just a standardized small satellite specification. So we break up all of our, the smallest possible unit for one CubeSat is a 1U or 1 unit CubeSat, which is 10 by 10 by 10 centimeters, and it's around 1.2 kilograms. 10 by 10 by 10 centimeters is about the size of like a really small tissue box. And the reason that we chose that size is because it's one of the smallest sizes that you could use that the US government can track using radar. The standard size is also really nice because it allows them to easily fit onto any kind of rocket. For example, a lot of rockets have to fill their payload space with ballast, for example, like rocks or sand. And that's in order to balance rocks to make sure that when it goes up, then they don't tip over. And rather than just sending rocks into space, my professor thought it'd be nicer to send like actual science experiments. So that's what they did. And CubeSats are nice because they also lower the barrier of entry to space. So clearly they're a lot smaller, so they're much cheaper than larger spacecraft. They have a shorter development cycle. Most of our CubeSats at the CalPoly CubeSat Lab take around 2 years to 3 years to go from the initial mission design to launch. And they're a lot simpler that even high schoolers can get involved in space now, which is a really awesome thing. And what can CubeSats do? They do all kinds of cool science. We'll talk about a bunch of missions throughout the slideshow. Tech demos for new and untested technologies. A lot of education projects since anyone can get involved now. So they can really do just about anything. So the photos here are actually 3 CalPoly CubeSats just spanning through the years. So the one in the middle of the frame is CP1, our first CubeSat. The second one is a 2U, LEO, CP9, our 9th mission. And the one on the right is ISX, a 3U. It's our 11th mission. Right. So just a little bit about how these CubeSats work is they are like these small little cubes, and they get packed into this thing called the deployer. On the bottom left photo, you can see the deployer right there. It's essentially like a jack in the box. You take the box, stick it inside of the bigger box, and has a spring, and when it's in space, when you open the door, they'll just get shot at. And since these CubeSats are becoming so popular now, NASA is actually starting to fund a lot of companies to do private launches. So everyone probably knows SpaceX. They have like the Falcon 9 and the Falcon Heavy. And we had a couple of our spacecraft launching those rockets. We also have another interesting rocket company is Virgin Orbit, where they're doing, they have a rocket called Launcher 1, and it drops off the side of a plane, and then it gets launched into orbit from there. So we have one of our satellites on there as well. And we have a cool video. So you can get launched from a rocket, or if you like see the little dot on the screen on the video, we can also get launched off the ISS. So that's one shot of, this is a stereo. This is one of JPL's missions. I'm getting launched off the ISS. And I have another one with 3 CubeSats getting launched off, and you have to admit, it's pretty cool. Just getting to see that. Yeah. So just a little bit about the CalPoly CubeSat Lab. It's a student-run lab. It was created in 2001. Just keep in mind that Dr. Jordi Puig-Suari, he was a CalPoly professor, aerospace professor, who co-founded the CubeSat specification at CalPoly 2 years earlier with Bob Twiggs at Stanford University. So they created the standard, and then they're like, oh, this is awesome. We should create a lab to show people that this can actually be done. So we currently have around 80 students, 90% of which are undergraduates, 10% are graduate, and we have 2 faculty advisors and some staff. And we're currently working on our 12th to 15th missions. So we launched 11 so far, and we're kind of like got to a point where somehow ended up with 3 missions going on at once, which we tried to avoid, but it happened.
That's a huge number.
Yeah, yeah. And we do everything from the early mission design and analysis. For example, we might get a proposal, or we'll write a proposal for a full mission. We'll do the hardware mechanical design. So pretty much everything you see on the spacecraft was built by a CalPoly student, or designed and built by a CalPoly student. So manufacturing and hardware testing. We also do the assembly and launch and environmental testing. So, you get all these parts, we put them together, and then we have to like test to make sure that it's not going to just fall apart in the rocket. That'd be bad. And then we do flight operations. So kind of, you see like in the middle 2 photos are a photo of completed spacecraft, and then that's kind of like they're assembled in our clean room. That's what the clean room looks like. You have to dress out, wear a hat, and wear the smocks and all that. And then the photo on the right is our Quad Yagi ground station with a photo of bishops in the background. So lots of open space for at CalPoly. So kind of a little bit of my experience at CalPoly's in the PolySat program was that I joined in my first year. So that means I'm starting my 4th year at PolySat and my 4th year at school. And when I joined, I had no experience. The only experience I had in high school was I was on my first robotics team. So we built these small robots, and they drove around on a course and did tasks, but nothing like PolySat. I first joined on the electrical team, so I did a lot of the flight and ground hardware design. I've designed side panels, and if you look on the bottom right photo, that's the flat sat for ExoCube, and I designed the side panels and the little connectors that connect the side panels to the main stack of boards. And we do many hours of design reviews and testing. So if you send it to space, you can't bring it back easily. So you have to make sure that it works before you send it up. And then now that I've been on the electrical team for a while and I know how to do computer science, I started to do a lot of software interfacing between the hardware and the software now too. And then so I spent a year on the electrical team. I still work on the electrical team, but I was my main thing for a year. And then I became the ground station lead 2 years ago, so my 2nd year at CalPoly. And basically what I did there was I maintained CalPoly's 3 stations. So we have 3 antenna arrays at CalPoly. We have a single Yagi, dual Yagi, and quad Yagi, which is more antennas per station. And it takes a lot of work to maintain those to make sure that they're always up. And I also assisted with the ham radio and station training to make sure that people understood that they shouldn't be sending signals at the library because it's just a waste of power. And then last year, I was the co-lab manager for the CalPoly CubeSat Lab, and I was managing our 7 flight missions. As I said earlier, 3 are in development, 4 in orbit. I've been doing a lot of systems engineering, and I didn't realize it, but coordinating people is very difficult, especially when the lab becomes, around 80 people. So yeah,
that's a huge number.
Yeah. So that's the PolySat experience. It's been really exciting. And then, okay, so I'll talk a little bit about JPL. So if people aren't familiar, JPL is probably one of the most renowned laboratories on the planet. They're a NASA field center managed by Caltech in Pasadena, California. That's right next to where LA is. And they have so many awesome missions. I listed just a few here that might be the most popular, and then one kind of oddball because people don't really know JPL for their CubeSats, but they do CubeSats really well. So everyone probably knows Voyager, Cassini, Nguyen, Juno, and MSL, or the Curiosity rover. Those are the 4 photos on the right-hand side. And they also do CubeSats too. So one of our missions, I think it was CP8, IPEX was a JPL-sponsored mission. So that's one CubeSat that they've done. And they also have a CubeSat called Asteria, which was had a lot of the components that went on Marco. And Asteria is a cool mission because what they did is they had really nice sensors on board that allowed them to track exoplanets and measure their transit across sun, so they can do exoplanet transits with their sensors. So something that would usually cost like a multi-million-dollar spacecraft to do, they were able to do with the CubeSat.
I'm having difficulty in hearing your voice.
Oh, sorry. So I was just talking about Asteria. What they did with that mission was they were able to measure the transit of exoplanets in front of their stars in order to see how far away the exoplanet was. And usually that's something that only a multi-million, lots of multi-million, hundreds of multi-million-dollar satellites would do. But they were able to pack all that into one tiny 6U CubeSat. So that's JPL. And just sort of to lead up about what I did in my summer at JPL, we'd have to understand that I wasn't working on the InSight mission. I worked on the Marco mission, which flew with InSight. So maybe just a little bit about InSight. So InSight is NASA's lander that has instruments to measure the Martian subsurface. So it's a lander because it doesn't have wheels, so it doesn't go anywhere once it's landed. It sits there and it does its magic and all its science. And it landed. It performed its landing using landing rockets, so it didn't have some of the cool air tram things where they hover above the surface for a couple seconds and then lower the rover down. No, it's just a lander. So. But it's doing a lot of cool science about measuring the Martian subsurface, and learning about how Mars was formed also helps us out a lot here on Earth, because it helps us understand how the Earth was formed millions and millions of years ago. So this is just a short clip about what the InSight landing looked like. So pretty cool, lots of boosters. Yeah. And then we'll talk about Marco. So Marco stands for Mars Cube 1. They consist of 2 near identical 6U CubeSats. We called them Marco A and Marco B, or Flight Model 1 and Flight Model 2. But they had this cold gas propulsion unit. Essentially, if anyone has ever seen the movie Marco, they use the same, very similar materials that you find in fire extinguishers and just blow it up the back in order to do all of our trajectory maneuvers. So kind of based off that, we called them Wally and Eva, because they had that scene in the movie where they used fire extinguishers to fly around space. Yeah, so that's fine. Marco was a technology demonstration for the mission, so it wasn't crucial to InSight's success, but it did provide a lot of help in getting InSight to land on Mars successfully. So it helped. It was the first CubeSat in deep space. So the tech demo that we were mostly showing was showing, do CubeSats work in deep space? And since CubeSats had never been to deep space, no one really knew if you could navigate a CubeSat in deep space, because it's very rare. Actually, it's never happened where you'd had something the size of a briefcase with some rockets strapped to the back and a radio, and we're not sure if we can talk to it that far. We didn't really know. We weren't sure. So a tech demo like this just proves the concept that a mission like this is really possible, and we can do it for less than $20 million compared to InSight, which costs it close to $200 million. Yeah, so that's the second tech demo that Marco is responsible for. The last one is called the Bent Pipe Relay. bent pipe is this telecommunication concept where rather than talking directly to the source, for example, InSight when it's landing, rather than talking directly to the Earth, it will relay its data through MARCO or through the MRO, which is the Mars Reconnaissance Orbiter. And that's because during the entry, descent, and landing, to my knowledge, I think InSight is being covered by its heat shield and like the shroud from the cruise stage, so it can't communicate with us with its high beam transmitter, high power transmitter. So it can only use a lower power one that it uses to communicate with the satellites around orbit or MARCO flying by Mars, and then we'll just relay the data. So during the actual EDL, we actually got all of the InSight data perfectly, and we got it before anyone else on Earth knew that InSight landed. So that was like a really cool experience because we can see that InSight is landed because it has these really noticeable beeps every time it does a significant event during its EDL. And we saw the beeps, and we saw that it landed, and then we didn't say anything because we wanted to make sure that the InSight team was ready too. And then 20 seconds later, everyone cheered, and we're like, yeah, but we knew beforehand. So yeah.
So I have one. Can I interrupt you? I have one question here. Like,
yeah, for sure.
Is it the InSight is always inside with MARCO, or it only receive the data when it's over the MARCO?
We only really talked to it during EDL. There was one test when we first got launched just to make sure that it worked, to my knowledge. But after that, we just flew side by side, not really communicating until we finally got to Mars.
Okay.
Yeah, and then during InSight's EDL, our primary missions were to take a photo of the Mars flyby. So that's the photo on the top right. Yeah, it's pretty awesome. And then our second task was to relay InSight's landing telemetry. So that's like actually getting the data from InSight's landing and then sending it back to Earth. Yeah, and then so I have a short video I can show you guys. This talks a little bit about MARCO, basically what I just said, but it has really nice visuals that will help everyone. It'll make more sense about what it does.
Communicating between Mars and Earth requires a complicated choreography, with everything in the right place at the right time. Sometimes hours can pass before information is relayed from one planet to the other. That's why when NASA's Mars InSight lander launches this year, the rocket will carry 2 tiny satellites on a technology test of their own. Meet Mars Cube 1. MARCO, NASA's first CubeSat mission to deep space. These briefcase-sized satellites will travel separately from the InSight lander while they test out new miniaturized technologies. And if they make it to Mars, they could relay information back to Earth about InSight's descent and touchdown, and do it in mere minutes. Although this fast communication isn't crucial to the success of the InSight lander, this CubeSat test could change the way future spacecraft phone home.
Yeah, so that's MARCO.
Yeah, the video gives clear information about the question I asked.
Yeah. Yeah, so my experience at JPL was quite amazing, honestly. I'm like really humbled to like have such an amazing opportunity. But essentially, like day to day, what I did was I assisted with the operations process. So we just about every day had to talk to the spacecraft. It was on its way to Mars, so we got to the point where rather than having to wait 2 minutes for each signal, it got to the point where it got to 4 minutes and 6 minutes and then 8 minutes. Everything started to slow down. All the passes got longer. They started going from like 2 hours to 4 hours. You're in this room talking to the spacecraft, making sure all the systems look good, solving problems. So that's sort of like the day-to-day operations. But being a software engineer, I also developed telemetry software to assist with the operations process, try and streamline it, make it more efficient. That's on the bottom right is like sort of the GUI that I put together. That's the example GUI of the library I use. It's called OpenMcG. We also did a lot of telemetry analysis. So I had one other intern with me, Cassandra Craver, and she was an aerospace engineer. So like her main job was to like do a lot of the telemetry analysis, and I helped her out with that. And since MARCO is sort of untested technologies going to uncharted space, we had anomalies pop up as expected. So we had to help out with the anomaly resolutions and trying to figure out what went wrong and make sure that doesn't happen in the future. Yeah, and it doesn't say on the slide, but I also want to thank like there's like the Marco people, all the folks at JPL, but we also had a team at CalPoly, and it's one of the first times where we had a team that was integrated, not at JPL, but worked directly with the core operations team in order to do operations from CalPoly. So essentially we sent CalPoly data, some of the flight telemetry, the data from the spacecraft, and they analyzed it and got us some really helpful like future steps forward from that data. So that's like another thing that not everyone talks about, but it's a pretty important aspect to the collaborative aspects about CubeSats. And then during the EDL, or the Marco flyby on November 28th, what I did was I was on console. So if you look at the middle picture, that's kind of the space flight operations facility. I sat in like the bottom right corner of that space, but I was in charge of checking the Marco B systems and the EDL data accountability. So in lieu of just like looking at the screens and making sure that Marco is healthy, I also had to make sure that when Marco started transmitting the landing data from InSight, that it came, hopefully all the pieces came. Because if we missed any pieces, we would have to tell the spacecraft to retransmit everything before it resets and we lose it forever. So thankfully got it in the first try. So yeah, just some photos. The bottom left, I had some folks from my lab come down to visit me at JPL, which is really nice of them. And then the photo on the top right, we got a chance to go out to Goldstone, which is one of the 3 deep space network facilities. So there are 3 deep space DSN facilities, deep space network, that basically are like the backbone to any deep space mission. There isn't really any other system like it in the world. They have one station in Madrid with like a bunch of dishes, one station in Canberra, Australia, with a whole bunch more dishes, and one in Southern California, like sort of like in the Mojave Desert in Goldstone. And they have these ginormous 34 and like 70-meter dishes that we get to talk to our spacecraft with. And then sort of for my last thing I want to talk about in this slideshow is what I did this past summer at Liger. So the Liger Leadership Academy is this residential scholarship academy in Cambodia, in the capital, Phnom Penh. It's 110 students, ages 11 to 18, and they're like, this academy is like super focused on project-based learning, which is like a super awesome thing. CalPoly also preaches sort of the same message. They always say, learn by doing. So there were some students, there was a group of students at Liger that were motivated and super interested in CubeSats. So they formed LigerSat. They like reached out and found some people from the States to help them out. And then they also found us, CalPoly, the creators of the CubeSat, I guess you can say, and asked us for help. So we did.
Yeah.
So Dr. Four was sort of the main, like, she's like the big brains behind a lot of these types of missions. She originally came from Japan. She's not from Japan. She's a French woman, but she came from a program at the Kyushu Institute of Technology, KTech, and they are really well known by a lot of people in Nepal because they helped build Nepal SAT-1, which is one of the first. Yeah. So this is since then she's moved. She actually teaches now at CalPoly, and this is like one of her first projects to like bring that to the States because we don't really have that much. We don't have too much of that here. So what we helped them with when we were in Cambodia was we like helped them put together a really solid CubeSat strategy. Like, what are the steps and how, in which order should we do the steps to be most successful and do it in the least amount of time? So while we were developing the ground systems, we were writing proposals and grants to like start the CubeSat because unfortunately everything revolves around money. So we need to get money. And at the same time, we would create the operations training program and just work on getting a lot of students like familiar with ham radio, interested in radios, honestly, and just like getting that process and training ironed out. And then hopefully by that time, when we have a lot of people who are interested in space, then we can begin the CubeSat design and the build. One of the things that we found really tough over there was that Cambodia isn't really a nation known for having like a lot of infrastructure that's like well ironed out like it is here in the West. So when they were first getting set up with this sort of project, a lot of this found out that like they see a lot of resources online that you need to get like licensed to use amateur radio, but Cambodia doesn't have any system for licensing people. So I think they were like the first high school students to get their amateur radio license in Cambodia, like a couple months after these students at NPIC, which is the National Institute of Technology in Cambodia, did. So, right, getting like sharing that love for amateur radio and technology is like a great thing. So, you know, we're like trying to work out like what is the process for a country that doesn't have any process for this yet. And then that's like one side of it for the like the human aspect. There's also like the actual station aspect where like if we have a station here and we set one up that can do transmit 100 watts, in the future they might want to do 500 watts, or in the future they might want to do 1,000 watts to like talk to something at the moon. How are we going to license their station? There's like you can basically just set up a station anywhere, I guess. So having a way to, you know, properly license that is really important. That really they don't really have the infrastructure for that yet. So helping them set that up is important. And then
it's a great problem in Nepal too. Yeah.
Licensing, yeah. It's very difficult. Yeah. And so just a little bit of the ground station. It's currently still manually controlled because we're getting together some funds in order for them to buy a rotor so they can not have to hold the antenna, you know, while they like want to track a spacecraft. We're sort of like telling them not to do it when it's like cloudy out in case there's like lightning. You know, that's not a good thing. So right now it's currently just manually controlled, but we're working on improving the station. But it has full transmit and receive capabilities. It operates in the UHF band, which is around 437 megahertz. And they're technically just the software that we gave them was it's open source software that CalPoly provides. It's like a reference implementation for a distributed ground station network. So it's sort of like SatNogs, but we just built it ourselves because we do everything in-house. So if we just like look at the photos, the top right is just me training some of the students about how to use some of the equipment that they got. Same with the second one going down from that. The bottom left one is a shot of the team after we finished building our antenna. And then the shot on the right is Dr. Four showing them how to track it based off like the compass that you can use in your phone.
So what measuring technique do you use to measure the impedance?
Oh yeah, so we had an SWR meter and we did it by hand. So we, since it's a Yagi, it's pretty easy to adjust the impedance. So by adjusting the spacing between the driven element and the first parasitic element, it's like all the little cross rods on that long bar, you can change the matching. And we got the best SWR we got was like 1.2, which is pretty good for a 100 watt.
That's good.
It's pretty good.
So did you also simulate the antenna?
No, so I haven't taken the classes to even know where to start with that. But luckily online, there's like all these resources and just reference design on how to get started with the Yagi. So one of the ones that I found online for a 11 element Yagi, and they had all of the Smith charts simulated and all of the like directivity and all of those parameters already calculated. And I was like, this looks like a really good design. We should just build it and just try it out. And it was awesome that it worked on the first try. Yeah.
So what's the frequency?
The frequency is UHF. So it's around 437 megahertz, plus or minus like 10 megahertz.
Okay.
Okay. So thank you for a nice presentation. So I have a few questions for you. So yeah, if it's okay, I can ask some questions to you. Okay. So for my first question is, like, can I ask, how did you get into the GPL?
Yeah. So yeah, that wasn't just like a fluke where I just applied and they're like, oh yeah, we like you. No. So that was a great opportunity because Andrew Clash was the chief engineer for the Marco mission, and he's collaborated with CalPoly numerous occasions on previous projects. And since Dr. Bellardo knew him, and they were like trying to start this new thing where we would collaborate on operations. That's just something that's no one has really done before. They said, why not give it a shot on Marco, which is also sort of untested. So they like were negotiating for a couple months, and then we finally came to a spot where we had 2 interns, me and Cassandra, go to JPL and intern there. and Cassandra actually stayed for an extra quarter while I went back to school. So she's behind a quarter, but she got some extra time at JPL, and we had the team at CalPoly also helping out at school. And then the actual like EDL day was not planned during the initial stages. It just happened like once school started, like 3 months after. They're like, I guess there's enough room for everyone to join in. So we were able to sit on console in the control room while everything was happening. It was quite amazing. So yeah, just connections really.
Yeah. Okay. So I'd like to ask about your view, the difference between working in deep space missions and versus working in Earth orbiting satellite missions.
Yeah, it's a huge difference. Everything, well, I mean, it's pretty clear, but everything once you put into deep space is a million times harder. If there's a problem, you have to wait, right? It takes, depending on how far away it is, you can wait from 2 minutes to an hour for your signal to get back. All of your systems have to be more well developed. You can't, like, when things are around Earth, it usually doesn't get colder than like -35 degrees Fahrenheit to like, it never goes above boiling in orbit. And your communications get a lot harder because you're so far away. You need a really good radio, and in order for your signals to even get here, your spacecraft has to have a pointing capabilities built in, or else you'll never hear the signals. And for that to happen, you have to have all types of fail safes built in case those systems fail for whatever reason. And if they do fail, you might lose your spacecraft and not know where it is. And in order to make any of those things possible, you have to have all the infrastructure that, like, basically only JPL has. Like, JPL is the only institution in the world that has that kind of infrastructure. They own the DSN. So, it's a lot of work. Everything's just more difficult. But compared to like an Earth-based mission, like, everyone's built up the technology required to make that happen, that it's so easy now. Like, you can just put together a sat-nav station and talk to something in space. And that was the joy of working on Marco, because now we can really analyze and see, like, what's really like the core set of stuff that you need in order to make a deep space mission possible. And from there, we can only build, we can only go up.
Okay. So would you like to share about the platform you use to develop telemetry analysis software? Like, is it okay to share?
Oh, yeah. So it's called OpenMcG. It's developed by a couple of guys over at NASA Ames. And it's just a web-based application to help you visualize all the data. So you set up all the databases in the backend with all the data, and you have to provide, like, you have to write a little bit of code to provide the interface between their visualization software and your database. But once you get that working, it just gets displayed on the screen really nicely. And that's one of the nice things, because at JPL, I was pretty sure it was true. I got that vibe. And at CalPoly, it's not as true. But like, a lot of times you'll see that every time you start a new mission, if they're spaced very far apart, everyone just ends up rewriting all of their software, which is just a lot of wasted man hours. So kind of like standardizing all of that into the same sort of same set of tools is very helpful in terms of, like, if you have to pay people or, try to get more done in a year. Yeah.
Okay. So, like, do you prefer COTS software, like for small or pico satellites, or you prefer space qualified hardwares?
So for LEO, for low Earth orbit, I guess just any orbit around Earth, COTS is the way to go. There's almost no reason that you would have to get like a super official, like fully certified piece of hardware or software, because we've seen COTS been tested hundreds, if not thousands of times in low Earth orbit already. Like, we've already launched 11 CubeSats, all flew COTS parts. The only parts that were hardened or certified are like maybe like 1 or 2 connectors, because they just had to stick the box into the box and they didn't want to change the connector. So at that point, there really isn't any reason to go for like super proprietary stuff, because it's so much cheaper. It's easier to use. You don't have to, you can buy it just about anywhere in the world. You don't have to sign like an NDA just to like see the data sheet. So, just COTS is the way to go. I think I saw a couple CubeSats that they like their main processor is like a stripped down Android phone. So that's definitely COTS. Yeah. For the people who don't know, COTS is consumer off the shelf. I think there might be an S. Maybe it's stuff, consumer off the shelf stuff. But yeah.
Yeah, I would rather say like COTS with space verified or space qualified.
Yeah, essentially.
And that would work.
Yeah.
So what about open sourcing hardware and software? Like, do you also prefer open source software hardwares or?
Yes. So I guess I come from a very liberal, like computing background. Like everyone at my school, like we do everything open source essentially, except our homework. I guess it's like the one thing that's not open source. Or else your peers can see your homework, which is not good. But besides that, yeah, I'm a huge open source guy. So like the CalPoly avionics, our flight computer runs Linux, and our ground station runs on all of our servers, which run on Linux, and they're all open source. So like if we have to go somewhere and set something up, like we bring a Raspberry Pi, and that's our ground station essentially.
Okay.
And our communications protocol, rather than having to reinvent the wheel and create our own protocol, our spacecraft actually shows up, like we give it an IP address on the campus network, and it shows up as a server on our campus Wi-Fi. So if you wanted to, like you're in class and everyone else is busy, or they went home for winter break, so you're in class or at home and someone needs to operate the satellite, you can just connect to the CalPoly network and then just operate the satellite from home. Like, how cool is that?
Okay. So
like,
what about your advice? What about your advice to the students from schools and colleges who can't afford to build CubeSats? So
just my advice for that is, like, I mean, I can have a lot of advice for that. Probably my biggest thing.
Could you share some? Yeah.
Yeah, I would start at like stay motivated and like look at the big picture, because something that I've ran into recently is because we have like 5 projects going on at once, is that like day to day it looks really boring. You had to test this one board for 2 weeks just to see if it's working. And it turns out nothing is working. But in the long run, right, like if you get this thing working, maybe it'll take you a month, maybe it'll take you a year, but at the end of the day, you're gonna have this thing in your hand and it's literally gonna go to space. It's like a really awesome experience. So that's like one of the things I would teach you. Another one piece of advice. Another piece of advice I'd recommend is just start small, because like you can't run before you walk. That's a really good analogy. So CalPoly, before it started its first CubeSat, like the first years of the lab, they didn't build CubeSats. The first thing they did was weather balloon experiments, because it's like the same sort of technologies that you would need to go into it, just less complex, right? Because it goes high into the altitude. You need a way to track it. Rather than using a ground station to track it, you might need to use GPS, right? You still have to talk to it, so you can probably use a radio of some sort. You need something to process all that data, so you'll have a flight computer, and you'll need something to start simple. Start with like a weather balloon, right? Start with and sort of work your way into a CubeSat. And then my last piece of advice, because a lot of people forget about it, is that when you're starting a CubeSat program or if you're building a CubeSat, try talking to CubeSats first. Try the operational experience, because a lot of people just jump into the CubeSat, they get their CubeSat launch, and then they don't have a ground station. And then, like, we have this thing in space. What are we gonna do now? So, and the nice thing about the ground station is it's also really great for outreach, because it gets people excited about space, and that's like the whole goal of what CubeSats are, really. Yeah.
So yeah, like how difficult is it to get amateur radio license in your country? Like it's really hard for us to get license in amateur, especially in UHF band transmission. So,
yes. So
same in your case, or it's quite
in the
easier in your
US,
case?
it's very easy. Like we can just look it up online, or I mean, not really even that. We can go to Facebook and Google ham radio. They call it the ham cram because since the question bank is fixed, people just like show up to the test 3 hours early and just memorize the questions and then take the test. I mean, honestly learn how to do this stuff first. Right? But for the technician license, I would say it's okay. If you just want to get interested and you want to talk to someone, that's all right. But you can really just go to Facebook and Google HampCram or search HampCram and find one nearby and then just go. At least at CalPoly, we offer the amateur radio test basically once every couple months. So we try to get everyone, just about all the members in the CalPoly CubeSat Lab are licensed because you need a license in order to operate the CubeSat. So we're like, just get your license. But I understand, like, yeah, if you're in a country like Nepal or Cambodia, it could be very difficult, and that's when I would like recommend, like, reach out, like talk to someone at the CalPoly CubeSat Lab, talk to someone at the FCC, or if you have a Ministry of Telecommunications, like try to get that ball rolling, because trust me, you're not the only one who's like trying to get into that. Everyone's getting excited about these kinds of technologies.
Yeah, it's quite easy to get in VHF band, and like it's NHF band, but it's quite hard in UHF band here in Nepal.
Yeah. All right. Yeah.
So what kind of logistic do you perceive that a student team in Nepal might encounter?
Like logistic issues. I mean, besides the licensing stuff, probably the next most difficult thing I would say is trying to find a launch, probably. In the US, it's made really easy because we have this thing called the Alana program. I think recently they renamed it to the CubeSat Launch Initiative, CSLI. Essentially, if you're an educational institution, NASA, if you apply, NASA will pay for your launch, essentially. So, like, you're put on a rocket, and as long as you meet your deadline, then you'll send your satellite to space. And that's just something that is like hard to come by outside of the US. That's just how it is. So there are a lot of programs. Dr. Four probably speaks better about this, but at least on the Japan side, they're working really well, really heavily with a lot of countries in Asia about trying to get launches with them too. They have another program. So if anyone's interested, you can shoot me an email, and I can put you in contact with her.
Okay, so I'd like to ask about your advice. How a non-spacefaring country, how a student from non-spacefaring country can get help or can start building their own satellite, despite of having their own facilities, lab facilities, testing facilities, blah blah. So your opinion about it, or your?
So just my advice for that is, like, you know, if you really want it, you can definitely achieve it. Like, all of the facilities exist. At least you don't have to create something brand new. All right. So, like, if you really need the testing facilities, and you're like already putting together stuff, hopefully, then there isn't a problem with reaching out and just asking for, like, hey, I know you build CubeSats, when do you get your stuff tested? And you might even come across a lab that hopefully has a clean room. For example, at CalPoly, we're really lucky to have a clean room and have space for a lot of environmental testing. We do shock, we do vibe, we do thermal vacuum testing, all on campus. And funnily enough, people like JPL, and they'll drive 3 hours up from Pasadena to San Luis just to test it, because they don't have to wait in line. They just come up, test it, and then drive back down, rather than having to wait in line and pay more money in order to test their stuff. So, I mean, if you're abroad, I'm sure you can find lots of places to test. It might require a flight or a really long drive, but you don't have to test everything environmentally. You don't have to test your stuff until it's fully assembled, essentially. So that's like, assuming it works, right? One-time trip, integrate your payload, your CubeSat into the rocket, and then you're set to go. Right, but like a lot of it is just starting. I think is the most difficult part. Once you've started, then you have the momentum to finish the job.
So we have a question from the audience.
Yeah.
So Nishal Khanal has asked, can small countries like ours build interplanetary CubeSats like Marco, or is that still a very complex mission?
Yes. So I would say it's a very complex mission. I wouldn't say that there aren't any university programs out there that aren't doing it, but the better way to phrase it is there aren't any university programs anywhere on the planet that have successfully done it yet. So I would say start simple. Like especially at my lab, we're still trying to figure out like how we can make our Earth-based satellites better. So right, without any of the infrastructure or the team, like for Marco, I mean, I'm sure at least 100 people, more than 100 people, 200 people must have touched the spacecraft before it went into orbit. Like the radio alone had like a team of 100 people working on it. So I wouldn't say don't dream that one day it could happen, but you got to take big steps before we can get there. Yeah.
Okay.
Yeah.
So would you like to share about your future missions?
Yeah. So the current ones in the pipeline, they're sort of reaching the end, are ExoCube 2. It's a mission that we have a payload from NASA Goddard with a mass spectrometer. So rather than having to accelerate particles into the spectrometer in order to measure the density of atoms in the atmosphere, we're already moving at like 7 kilometers per second. That's the particles just hit the spacecraft. So we just eat a few of those, we catch them in space, and we will measure them based off that. So that's CP12, that's our 12th mission. We have our 14th and 15th missions are sort of based on the same thing. It's called AID. It stands for Aerodynamic Drag Experiment. It's a mission that we're doing with Purdue, and essentially Purdue is providing us with this big snail that we deploy, and the hope of it is to try and to make the orbital lifetime of CubeSats shorter. So, minimizing that space debris, problem that everyone always brings up about CubeSats. Like, you're just sending trash into space. Well, if it can deorbit within 2 years, or if we can say the mission's done, we're going to deorbit, then that would solve the problem really easily. So that's like one of the missions that we're doing. Besides other missions in the pipeline, there's a call for proposals for Artemis right now going to the moon. So that's like some stuff that's I'm sure some people in our lab are looking at. That right, the next step from Earth is the moon, I guess. Yeah.
Okay.
So we have another question from the audience.
Yeah.
So can you explain about the hardware specs of the ground station that you build in the Liger set?
Yeah. Actually, I can go back in the slideshow and we just look at a photo. Here we go. So the nice thing about using the amateur radio band, assuming the FCC and the AIRU, this International Association of Amateur Radio, I got that completely wrong, but there's an association internationally that manages the amateur radio bands. The nice thing about using the amateur radio bands is that all of the hardware already exists. You don't have to make a new radio, like a new design, and you don't have to buy something that costs $12,000 for a radio because you're like one of 5 people in the world that actually need one. So since these things are so widespread, I mean, we were able to pick up some of these radios and all of the components for it in Cambodia. That's like the nice thing about amateur radio. So the radio that we have here is a UHF VHF transceiver. It's an ICOM 910H. Has 100 watt transmit capability on VHF and 75 watt capability on UHF. We have a what's it called? A SWR meter in order to make sure that the antenna is always matched. Like if someone dropped the antenna, then we should know immediately. So we'll usually have that in line as well. And that will go directly to the antenna essentially. And then everything on the digital side is just the radio and a USB connection to a computer. And we do just about everything on the computer to minimize the cost and just to minimize the complexity of the system. So if you're looking at technical aspects about the software side, there's no TNC. It's a terminal node controller, which does the demodulation from the audio signal from the radio into digital bits. We're using the sound card on the PC to do that. So we're using Direwolf is the name of the software. There's a couple other ones that you can look at. And the team also has an RTL SDR. So if you want to get into ground stations very cheaply, you can buy this little USB dongle that has a USB on one side and a radio connector on the other side. It costs $25. It can do just about every band. So the only problem with it is there's no transmit, but I mean, you can always start with receive first. It's receive in and itself is hard enough. So That's like the kind of the radio set that we have. We had, you know, ICOM, amateur radio, and SDR. Yeah.
Okay. So I think we have come to an end. So before leaving, would you like to share some of your experience joining Space Talk?
Yeah, it was fun. I don't get to talk about this too much. I usually just work all day.
Okay.
And everyone at school already knows I'm in this. So I can only talk about it so much before I start to annoy them. So, you know, I'm excited about space, and I'm glad that other people out there are really excited about space too. So, like, you know, you can achieve your dreams. Trust me. Like, I didn't think I would be here when I was in high school.
Okay. So yeah, thank you for joining our Space Talk series.
Yeah, thank you for inviting me.
Yeah, I think we have come to an end. So yeah. Thank you.
Right.
Talk to you later. We'll have some more. We'll have some more Space Talk series with you. Hope so.
Okay, so this was a part of SEDS-Nepal Space Talk series. We'd like to thank Justin and Mr. Saurabh Paudel for hosting the program. So we'll be having. So this talk program is focused for all the students, as well as professionals who is interested in the field of space and satellites. So this is kind of a bi-weekly series, no, not bi-weekly, fortnightly series. So we are hoping to conduct it in the next week. So if you are interested, if any students are interested, you can join SEDS-Nepal. You can join the talk program. All you need is good quality internet and curiosity. So I like to end the program. Thank you very much.
Yeah, I'd like to invite you to Nepal if you have time someday.
Oh, definitely, I have to visit.
Yeah, you need to. Okay, yeah, thank you.
All right, thank you.